Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be looking at another way of solving problems in classical mechanics, namely the way of dimensional analysis and scaling. So let us introduce this topic, the topic of dimensional analysis. We will start our discussion with some basics, right? So this whole idea of dimensional analysis depends on the study of dimensions, of variables and how these can be used to simplify the mathematical formulation of the problem. So the question is, what is the concept of fundamental? So we start with the topic of discussion, which is that of the fundamental dimension of variables. So this question we ask is, what is the concept of fundamental dimensions? What is the concept of fundamental dimensions? And we see that most of the variables such as force, density, velocity, etc., can all be represented in some basic or fundamental dimensions of can be broken down into fundamental dimensions of length L, time t, and mass m, right? Can be broken down into fundamental dimensions of length, time, and mass, right? And so these are my three basic variables, and similarly variables such as length, mass, and time, and also temperature, which is we denoted by theta, and as well as current, we denoted by I. So these are my fundamental dimensions, right? And what do I mean by fundamental dimensions? Variables which cannot be represented in the form of the other variables, the other fundamental variables, right? So they are independent in the sense that one cannot be written in terms of the other three, and that is the other three means the three we are talking to begin with, right? So that is what we call the fundamental variables, the fundamental dimension. So all the dimension of all variables will now always be represented in the form of these fundamental dimensions. We can associate these fundamental dimensions in the concept in linear algebra of the topic of so-called basis vectors. That is, any vector can be represented in the form of this basis vector. So similarly, any variable can be represented in the form of these fundamental dimensions, right? So then let us now talk about let us now talk about the so-called dimensional notation. Dimensional notation. So suppose we are given a physical quantity. So suppose we have a physical quantity Q, and the fundamental dimensions of Q will be denoted, the fundamental dimensions of Q will be denoted as Q, right? We use this notation, double bracket of Q as the fundamental dimensions of Q, right? And suppose if Q is dimensionless, so if Q is dimensionless, then we expect that the fundamental dimension of Q will be 1. It's not dimensional, right? So for example, if we want to find the fundamental dimension of velocity, let's say v naught, right? So this is velocity. We know that this is L over T, so length over time. So this is my fundamental dimension. Similarly, we are taking the case of the projectile motion. So in projectile motion, we also encounter the so-called maximum height. The maximum height, which is xm, which is L, right? And similarly, we can talk about acceleration due to gravity. G, the fundamental dimension of G is L over T square, right? So let us now look at a case of how to solve a problem using dimensional analysis. So let us take a very simple example, that is the projectile motion. So the problem says we want to find the maximum height of the projectile, right? So let us see how far we can go and find this, solve this problem using dimensional analysis. Let us see how far we can go. So suppose this question says, suppose we are interested to find the maximum height. Suppose we are interested to find the maximum height xm of the projectile, right? So we have the following, the maximum height of the projectile, right? So we have xm and this is tm, and then of course tm is the time of half the time of flight, the time taken to reach the maximum height, and in a simple projectile the total time will be 2 times tm, right? And this is the t axis and this is the x axis. And suppose, so now we see that the force which is acting on the projectile is the only force is the weight. We neglect any other force such as resistance and any other magnetic field and so on and so forth, right? So force acting on the projectile is due to its own weight, so this is minus m times g. And then we can also assume an initial condition. This is at t equal to 0. The initial condition is x at 0 is 0 and dx dt at 0 is v0, right? And we see that the maximum height in this case, xm, now will be a function of whatever the variables that we have found, which is m, the mass, the acceleration due to gravity, g, because that is what is appearing in the weight, and the unknown v naught. So these are the 3 variables we encountered. Let us assume that the maximum height is a function of these 3 variables. Now what happens is, we first need to show that these variables m, g and v naught can only be combined in the form of some ratio. it cannot be added or subtracted. These variables m, g and v naught cannot be added or subtracted to give the maximum height xm. Why is the case? Because let us, for the time being, let us keep this case as it is, and let us digress our discussion to a specific case study of why the dimensions has to be in the form of some ratio. Why not in the form of addition and subtraction? So let us, so we are digressing for 2 minutes. Let us now look at one case to understand this concept. So suppose the speed of the ball, we are looking at a simple example. So suppose the speed of the ball S, so speed is denoted by S. So speed of the ball S depends on the radius of the ball R and the time taken to move, right? So time taken t, denoted by t. Then I expect speed S to be a function of r comma t, right? So suppose if we had taken this function to be alpha r plus beta t, that is, we had taken the speed to be some linear combination of or which is addition and subtraction of the two variables r and t, then we expect that alpha times r should also have a dimension of speed s, and beta times t also has a dimension of speed s. Now we have further assumed that alpha and beta are constants, right? So constants, which means they are dimensionless. But if alpha times r has a dimension of the speed s, then alpha must have dimension of time. Otherwise, alpha times r will not have a dimension of speed s, right? So this has a dimension of time, and this leads to a contradiction because alpha is a constant, right? So this is a contradiction here. Similarly, we can find a contradiction for beta as well. So hence we expect that the speed has to be some ratio of r by t, right? And this ratio typically cannot be found using dimensional analysis. The proportionality constant cannot be found. This is from experiments, experimentally found, right? Okay, so then coming back now, so that is what I wanted to point out, that the dimensional analysis assumes that now the fundamental dimensions are in the form of a ratio, not subtraction or addition, right? So then coming back, so to the projectile problem. So coming back to the projectile problem, so we have the following. Now for the projectile, we can now assume that we wanted to find the maximum height. So dimensionally, the maximum height is now going to be some ratio. So let us say it is m times a, m being the mass and v naught being the initial velocity. So v naught times b and g times c. So listeners must not be confused with all these because these powers, because if the powers are negative, then these variables will go in the denominator and we will have ratios. So now we are assuming that the maximum height is in the form of some ratio. So now if we use fundamental dimensions argument, using fundamental dimensional analysis dimensions of xm, we see that on the left hand side the fundamental dimensions of xm is L, and on the right hand side it is m times a times velocity, which is L over t times b, times the acceleration due to gravity, which is L over t square times c. So now if we were to rearrange everything, we see that this is m times a, L times b plus c, and t times minus b plus 2c, right? And we now, if we were to equate the powers on the left and the right hand side, we see that the dimension of L on the left hand side is 1. So 1 is b plus c, and then the other two equations is minus b plus 2c is 0, and the third equation being a is equal to 0, that is the coefficient of mass. So now from here we have three unknowns and three equations. We can quickly find out that a is 0, b is 2, and c is minus 1. And if we plug all these relations here, we see that xm comes out to be, well, we want to plug all these relations here, m a b c values. Xm comes out to be alpha times v naught square by g, right, where again alpha is an experimentally determined quantity. So if we were to solve this equation of the projectile motion, we will find out that surprisingly the maximum height attained is some constant times v naught square by g. This constant can be found in this case, in this simple case, using our calculations or the Newtonian mechanics. But certainly it is, this dimensional analysis has provided our answers to very, very close proximity of the original method of calculation, right? So such a simple way of finding the solution, yet such effective way, right? So alpha is a dimensionless constant, right, which is found experimentally. Okay, here we can, in this projectile motion, we can make some arguments, we can make some observations. So observations are, if we look at this final answer, the observations are, the initial velocity increases by a factor of 2, and the maximum height, if the initial velocity increases by a factor of 2, the maximum height will increase by a factor of 4, because we have a v square dependence, right? So the max height will increase by a factor of 4, right? And similarly, the constant alpha can have to be found using experiment. So found experimentally, right? Okay. So experimentally, by observing various values of xm and v naught, right? So we find out what is the value of xm for various values of v naught, and then we can plug it into a relation to find alpha. And then the third observation, which is surprising, is that the xm does not depend on the mass of the object, does not depend on the mass of the object, right? So there is no m dependence. And this is also the reason that it is fair to assume that even a heavy ball or a light ball, when thrown under the action of gravity, will all arrive at the same vertical distance at the same time. In fact, this non-dependence of mass was one of the primary point of discussion during the time of Galileo, who did lot of experiments to indeed show that regardless of the mass, a lighter object comes when falling from a certain height will also be taking the same time as the heavier object, provided there is only acceleration due to gravity as the experiencing force. There is no resistance or any other force. Okay, so with all these observations, we can conclude that there is basically one limitations. We can find the answer using dimensional analysis up to a proportionality constant. So alpha is unknown. So that is the limitation in our dimensional analysis. Although dimensional analysis, the advantage being that this is a very, very simple technique to find the solution to the problem up to a certain constant of proportionality, right? Now let us look at another example, a slightly more complex example. The example that I have in mind is the case of the drag of a sphere, the drag on a sphere, right? So the goal is the goal this time is, so a sphere is a let us say a metal ball which is falling under the action, of course, under the action of a gravity, but also it is experiencing some sort of a resistance due to the opposing fluid motion. For example, the fluid could be water or could be air, if depending on what medium the ball is falling, right? So we want to find this resistance or the drag on the sphere which is falling vertically, right? So the goal is, the goal typically, why, what is the need of finding the drag on these objects? Because typically for these moving objects we want to minimize the drag, right? So the goal is to keep the drag on the designing objects as small as possible. The modeling assumption is that the drag force, let us call this drag force as dF. The drag force depends on the radius of the sphere. The radius of the sphere, we are assuming the falling object is a sphere, so we call this radius as r. And then it also depends on the velocity, the falling velocity v. And then of course we can assume that it depends, we are talking about the sphere falling through air, so we have to worry about the density of air. Let us call this as rho, to find out this air resistance. And finally we also have to worry about the dynamic viscosity of the air, which is mu, right? This is the medium viscosity. Right, now how are we getting all these variables to determine drag? This is coming from a little bit of knowledge about the physics of the problem, and that is giving us the various variable dependence. Now we can again set up the dimensional analysis equations. So I have that the fundamental dimensions of drag dF, remember drag is a force, so we have the dimensions of force. dF is the dimension r of A times v of B times rho of C times mu of D. This is the fundamental dimensions. And now since we start to equate the dimensions, we see that this is m LT minus 2 is r, is, after plugging in all the fundamental dimensions, we see that this is L times A plus B minus 3C minus D, T times minus B minus D, M times C plus D, right? And now if we start to equate the various equations, we see that for L we get the following equations: A plus B minus 3C minus D is equal to 1. For the dimension of T we get the following equation: minus B minus D is minus 2. And the dimension of M we get the equation C plus D is equal to 1, right? And now notice that we have four unknowns, and we have three equations, 4 unknowns and 3 equations. And we see that, which means that we can always find all the variables A, B, C, D in the form of at least one unknown. Let us say that the unknown is D. So we can find our unknown B to be, we solve these three equations: B is 2 minus D, C is 1 minus D, and A is 2 minus D. And when we plug it into our drag fundamental analysis, dimensional analysis of the drag, our drag comes out to be alpha times rho times r square v square times mu by rv rho to the power d. Mu by rv rho is a dimensionless group. We can check that this is a dimensionless group. Let us call this as pi, the dimensionless group. And so this is alpha times rho times r square v square pi of d, right? And so pi is a dimensionless group. We can check it. It's a dimensionless group. Okay, so then the conclusion is, say from let us call this as 1. So the conclusion is that typically we expect that here in this particular example we expect that this drag will not be if it will not in general depend on the power of a dimensionless group, but it will be some function, right, of the dimensionless group. So it's not just a power, right? So the conclusion is that df, the general solution df is not an arbitrary power of pi, but a function of pi. It is not an arbitrary power of pi but a function of pi. So in general we expect that df will have the following formula. It is r square rho r square v square times f of pi. All the constant of proportionality alpha etc are all absorbed in this unknown function f, right? Now it turns out that, so why we have assumed that the drag is depending on an arbitrary function of pi, not just power. Let us see why. So for example, let us say that so we are trying to figure out the reasons behind this form of drag being an arbitrary function of pi. Now suppose we want to find this pi, right? How do we do that? Let us say we want to completely determine the dimension of the drag or the formula of drag. We can do so by, of course, determining the constant of proportionality, and that is done using some experiments. We can determine the values of alphas, the constant of proportionality, with the coefficient, with the power di's. Say for multiple experiments or multiple observations, we see that alpha I and di can be written as, so df is rho r square v square alpha 1 times pi of d1 plus alpha 2 times pi of d2 and plus alpha 3 times pi of d3 and so on, right? So these are the observation values, and that I'm assuming for the time being that the functional dependence on pi is just through power law. So now we can further assume that this is our new function. So this is our function f of pi, right? Now we can check. So this is our function f of pi. So we can check that the drag can also be rewritten. If we had redone our dimensional analysis, we could have checked that drag could have been written as mu by rho times h of pi, right? So rather than having this function in terms of f in front of f, we could have this function in front of f. And now we can, so let us call this formula as 2, and we can call this the previous formula, this one as, or this one as 1. So 1 or 1 prime, right? So my claim is that 1 prime and 2 are identically equal. So 1 and 2 are identically equal, or we see that, so how to do that? We see that if we were to see, both are representing the drag. So both, when it must be equated to each other. So we see that, well, this is mu square, sorry. So we see that mu square by rho h of pi must be equal to rho times r square v square f of pi, right? Because both are representing drag. Now from here we can rescale, we can divide this mu square by rho on both sides, and to come to the conclusion that h of pi is 1 over pi square f of pi. So we have represented one dimensional non-dimensional function in the form of another non-dimensional function, and so we see that this is both the LHS and the RHS of this equation are non-dimensional. They are non-dimensional, and so we have come to the fact that the functional form is irrelevant. It's just the function, right? We could, as far as the dimensional analysis of a variable is concerned, so we can take an arbitrary function in front of this drag. So arbitrary function of the dimensionless group pi. So talking about arbitrary function, we could also have written drag df to be rho r square v square times g of re, where my re is the dimensionless group. So re is the dimensionless group rv rho by mu. So this is nothing but 1 over pi. So re in the fluid mechanics literature is denoted as the Reynolds number of the fluid, and re here is now, so we have written the drag force in the form of this new group g of re. Now this is a more helpful representation than the previous representation f of pi, because at least there are some experimental observations available to find this g of re in terms of this group re, which is non-dimensional. Right now, so one thing that I want to highlight is that g of re is related to f of pi, because g of re is 1 over f of re, right? So both are related. Now let me call this as form number. So this was my equation 3. I call this as form number 4, right? So we have just now through our discussion found two forms of the dimensional analysis, namely form 1 and form 4, having functions f and g. And now in the next module, I will show you how these two forms are, when to use either of the two forms, right? We will try to remove the ambiguity of which form to use for the drag force at what point of time. So thank you so far for listening.